Okay, so our last speaker before the break here is Chris Freye from Los Alamos National Lab. We're very happy you could make it. The floor is yours.
I was 0 for 3 last year for conferences, so I'm happy to be here too. So I'll be talking about PFAS today and GC-GC. That's going to be towards the end. We'll make it there. As Dwight said, I am from Los Alamos National Laboratory, or that one place in the Oppenheimer movie, if you guys have seen that. So why am I talking about PFAS when I work in high explosives? And I had that same question about a year ago. So we're over on the right side there in fluoropolymers, and we use them for a lot of things in the Manhattan Project, but we also use them in high explosives. And I'm going to particularly focus on one fluoropolymer today, KLF 800. It's made by 3M, or was made by 3M. So it's a chlorotrifluoroethylene and a VDF block there. But when you make fluoropolymers, you use PFAS, and they used a lot of different kinds of PFAS to make these fluoropolymers. And so we kind of made this, or pitched this idea of, well, there's PFAS contamination in the high explosives area, question mark. It's probably something to do with fluoropolymers. So for those of you who are not familiar with high explosives, we actually work with plastic bonded high explosives, or the other term is polymer bonded explosives. So we take these explosives and we encapsulate them in a polymer, which increases the safety of our explosives. For PBXs, it varies from different kinds, but it's about 5 to 10 weight percent polymer. We can also have plasticizers, we can have stabilizers in there. But why do that? Like I said, the big thing is safety, but we can also press and machine our explosives. So we'd have our powdered explosives, and in the top right there you can see once we turn it into a PBX, it forms these prills, or Nerds candy if you're familiar with that. Probably doesn't taste as good though. So how we make PBXs was actually developed in the 1950s by Lanel. And in 1954, we started using fluoropolymers. A DoD lab, talked to some people and the DOE and said, hey, these materials are really stable. You should use them in your high explosives. So we started using them. And looking back through the historical records at Los Alamos, from 1959 to 2003, we processed 91,000 kilos of fluoropolymer containing PBXs. Obviously that was more towards the beginning Cold War era, but that's still a lot of explosives to come across our desk. So what are the steps where we could get contamination? So for making PBXs, we take our explosive, we suspend it in a water bath and we stir it rapidly, and then we slowly add this lacquer that has our polymer and any other additives we want. Our polymer is going to crash out a solvent. It's going to coat our explosive and make those prills, and then we'll add more water to quench the reaction and separate out the PBX prills, and then we can dispose of the liquid to recover our PBX. As you can see, I've highlighted everywhere where there could be PFAS contamination. So there's a lot of steps in this process. And in the top right there, you can see my colleague. She's making a half-kilo batch of explosives. We could also make 10,000 pounds if we want at production scale. I know, it's kind of weird to say these numbers, right? for those of you who are not familiar with explosives, yeah, half a kilogram is really not that much. This is the high explosives area at Los Alamos. So not only do we, back in the day, we made lots of explosives. We still to this day do high explosives R&D formulation, so making PBXs. We press them, we machine them, and then of course we need to dispose of them. So I found this really cool picture in our archives of the guy, 1980s, standing next to a bandsaw cutting explosives, which I thought was kind of wild. I guess it was the Cold War. And then, of course, we detonate them to dispose of them because no one likes storing thousands and thousands of pounds of explosives. So not only do we have potential contamination when we're making our PBXs, but every single time we do a single step, there's more contamination or possibility of contamination. And this has been kind of like a big question mark. This is something that has entered the discussion point, and so we're not really quite sure where we are, but I'll give you an update on where we hope to go. Because I'm from the US, we have the EPA, or maybe not too much longer. But there are 40 EPA-regulated PFAS compounds for which a method exists. That's going to be HPLC triple quad. That's the gold standard. In 2024, that list increased to 150 compounds that shall be monitored, but there's not a method yet for that. Conversely, non-targeted, which is where a lot of my work lives and where this project's heading, for PFAS, there's 40 compounds, but really when we look at all the different possibilities, it could be 12,000, it could probably be a lot more than that. And we know that when we made fluoropolymers back in the day, or other companies made fluoropolymers, they use PFAS, and what we have seen is what they said they did is not actually what they did. That's maybe not too big of a surprise. So we want to go in with not any assumptions about what we should actually be measuring. We're kind of lucky. We're maybe hoarders of materials, so we actually have fluoropolymers from the 1950s and 1960s that we can kind of use as pseudo-standards, but we only have a limited amount of material. It's worth noting that for non-targeted PFAS analysis, there's a lot of research in the HPLC QTOF, lots of other MS. I've seen recent papers on 2D LC on PFAS. So that's where kind of everyone seems to be going. So with the non-targeted approach in mind, we had a couple goals here. We want to develop a non-targeted method for all PFAS. And so some PFAS is best analyzed via LC, some PFAS is best analyzed via GC, so we don't know what we should really be looking for. And I have this odd feeling that we're going to find more than we suspect, and so we want to make sure we cover the entire ground. Then we want to look through our fluoropolymers and our PBXs to see, can we fingerprint the material based on the PFAS content? And with that understanding, then can we go into the environment and say, right here in that dirt right there, that's from the 1950s when we did this exact process on this exact material. That's our pie in the sky idea. We're hoping to get there. So should we be doing LC, GC, or both? My friend said, instead of a question mark, I have like a greater than, and we can have the LC and GC people fight it out. Great thing about HPLC, it's almost universal for all PFAS. There's only a couple classes that LC is not really good at. And triple quad is already the gold standard, so going from triple quad to QTOF or IMS and QTOF, that's a simple, I say simple expansion. There's already prep methods for HPLC. There's really good papers out there. So there's that aspect. But then there's GC, which is really good for volatiles, namely the alcohol and ether derivatives. It doesn't work for all PFAS, namely the sulfonic acids or the sulfonates, unless you derivatize. But of course, we're at multidimensional, so we're going to be doing GC-GC. So we originally actually started with HPLC because that seemed like a natural evolution. And there's no methods on how to analyze fluoropolymers, neat fluoropolymers for PFAS. So there's lots of methods on if the PFAS is in the soil, or if it's in the water, or if it's in food. There's all these methods. So we kind of had to start from scratch. And for the EPA method, it's all about PFAS in water. And so we were thinking, oh, if we just take our fluoropolymers, we'll put them in water, that'll leach out the PFAS. The problem is it doesn't work, because what we found out is you have to first dissolve the polymer, and then you can add your water to cause the polymer to crash out. So we kind of get we dissolve our polymer, and then we add the water back, crash out the polymer, and we end up with really clean separations. And so it doesn't really matter what kind of organic solvent you start with, you just have to dissolve your polymer first. So this is our first separation, looking at that CalF800 and a PBX that contains CalF800. They said they used this weird sulfonamide, which we never found, but we found all these other great perfluorocarboxylic acids, namely PFOA. We also found PFOS. So kind of unexpected. This was using the EPA method for HPLC. We're using a Q-TOF as our detector here. We've since optimized our HPLC to really focus on fingerprinting of the molecules, but I'm talking about GC today, so that's another story. So jumping into the GC world, there's not a lot of papers on GC and PFAS. Back in the day, before LC triple quad became what it is now, people are actually doing GCMS on a single quad, and that was the gold standard for quantification. And we were thinking, between my collaborators and I, that GC might actually be an ideal technique for environmental samples because of the requirement that everything has to be volatile or semi-volatile. So by picking GC, we might be able to reduce our background matrix and get cleaner separations. The problem is getting materials on column is really challenging. So you have to derivatize, and we read a bunch of papers that say you cannot do PFAS analysis on GC unless you derivatize. And so we were thinking, I really don't want to derivatize. I want the robots to do everything for me. And so we actually overcame this problem using thermal desorption. So because we don't have a solvent, which is where most of the PFAS elutes, we don't have this coelution. We also have a cryotrap, so we get really, really narrow injections on the first dimension. And with the cryotrap, we can actually inject really large volumes, and essentially our sample introduction method doesn't really become an issue for the chromatography. So looking at the PFCAs there, I got a chromatogram in the bottom right corner there, and then the far right is a zoom in for mass channel 131, which is associated with PFAS, and our estimated limit of detection is 10 femtograms on column. And so that was kind of surprising, is we're now rivaling LC triple quad, but we don't actually have to do any sample prep like the EPA recommends, which is using SPE cartridges. So we're just as good as LC triple quad, but now we can inject way more and we don't have to do any sample prep. So we got really good separation when we were doing the GCMS on our standard, and so of course we're like, yes, this is going to be really easy. Problem is, we went to our fluoropolymer, and we could still see the PFOA, which we were expecting, but then when we zoom into the baseline, you can see it's, as previous speaker said, crap. It looks terrible. There's lots of isomers. And so when we were looking at our standard, everything is a linear chain. So what our separation really looked like was not that good. It was also the first time we had really ever analyzed this on GC. So we really didn't know what to expect. And what we found was it's really complicated. So we went to GC-GC. So there's our total ion current in the top left there, and then some mass channels. And we were thinking, well, the separation got a lot better, but MZ131, it could be PFAS, and so same thing for 69, but it could also be a lot of other things share those common masses. And so our little bit of head scratching, we're like, okay, our separation's okay, we can still do better. But I think it's time to transition to high-res mass spec to see, to understand what are we actually seeing here and how do we improve our separations. And the reason I say that is when you go look at the very limited publications on GC-GC PFAS or any of the tech notes, a lot of people are focused on separating PFAS from some kind of matrix. So what will happen is the PFAS will not be retained at all in the second dimension, and you get this really nice band of PFAS, and then you get everything else in your chromatogram. And that might be great when we get to the environmental samples, but right now we really need to delve in and understand what is all this stuff in our sample. Is it PFAS? Is it not PFAS? So transitioning from unit res to high res, we get this huge boost in selectivity. So mass channel 69, I've thrown some of the compounds that could be up there. I actually went into our software to calculate how many possibilities there are, and I guess there's 44 different things that mass channel 69 could be. Those are the four most common ones. But when we go out to the fourth decimal place, it can only be CF3. Problem is, when we go to high-res mass spec, we do lose a little bit of sensitivity. About 3x is what we've seen. But the great thing is we can really do unique data analytics. We can do AIML for fingerprinting. And today I'm going to talk a little bit about Kendrick mass defect, where we can take all this high-res information and kind of just simplify it to what are the structures that we're looking at. So this is our GC-GC chromatograms with high-res mass spec. So again, we knew there was going to be PFCAs there. But now we have all these other things that have mass channel 69 and mass channel 131. What are they? So this was kind of specifically looking at these mass channels because we know they're important. So what else could we be missing since we don't know what mass channels to look for? So if we sum away all our chromatographic information, we end up with 3,100 mass channels in our high-res space. And we can convert that to Kendrick mass defect. In this case, I've used CF2 as our repeating mass. And what we kind of came to the conclusion is there's a lot of really interesting information here. But because we're using electron impact and we're essentially obliterating everything that's coming into our mass spec, it's really not helping with the fingerprinting because in electron impact, a lot of isomers look like the other isomer. So how do we know which mass channel corresponds with what compound, and why would we do GC-GC before high-res mass spec? We could just put this into an electrospray source and get the same information. So we can do it on a per compound basis, a little bit of brute force. So I've picked two areas in the chromatogram that kind of looked interesting. And of course, there's no library match. That's not too surprising for PFAS. We'll either guess, repeatedly guess that it's PFOA, which we know it's not PFOA, or it will guess no library match. And there's just because the libraries aren't as extensive, and again, there's 12,000 plus PFAS compounds, and so the libraries will probably never fill up to that degree that we need to know. So what we can do is we can take those individual mass specs and turn them into Kendrick mass defects, and I've overlaid the Kendrick mass defect for PFOA. And what we found actually was the unknown number 2 does have a lot of PFAS-like. So it has the C3 or CF chain on it like you would expect for most PFAS. But for unknown number 1, we see a lot of chlorine splitting everywhere, but it's only one chlorine. And it does share some Kendrick mass defects with PFOA, but then it has a lot of other interesting ones, mass channels that we never would have guessed. And so we're still piecing the puzzle together, but what it looks like in that top left corner is we have a lot of the PFCAs, which we kind of already expected, but we're actually seeing monomers or oligomers of our polymer. So the reason we see that chlorine is going back to the CalF structure, it has a CTFE block, so it has a single chlorine on it. So there's a reason we see that. So is that PFAS? Is that not PFAS? Bad for people is all that matters, having chlorinated compounds. So we know there's these PFAS-like substances, but then there's this other unknown too that has this long carbon fluorine tail on it. So it's like PFAS, but it also has these other weird Kendrick mass defects. So it's not from our fluoropolymer. So it's PFAS, but we don't know where it came from. And we're not sure that that actually matters because it's still PFAS. So some future work that is going to continue. We really need to improve on our separations of PFAS molecules. And that's just, I think it's so new to the field that we really haven't, there's no paper you can go read. Like if you're doing petroleum or fragrances, there's thousands and thousands of publications. For GC-GC, I think there's maybe one. We definitely want to modify our Kendrick mass defect for non-targeted analysis so that we can subsequently feed that information into our AI/ML for fingerprinting. So if we took all this high-res data and we dump it in, is it really going to be fingerprinting in a way that we think it will, or are we just fingerprinting on different compounds that are not PFAS in our fluoropolymers? Another area of interest for Los Alamos is emission from the disposal of PFAS-containing PBXs. So like I said, we detonate. During detonations, we do actually reach temperatures high enough to destroy PFAS, but it's only for microseconds. So is that time long enough to destroy PFAS? We don't know. And then, of course, decomposition of PFAS in the environment. That is an ongoing area of research, I think, across the world. And so we'll hope to be talking about that here in the future, too. So some acknowledgements. I need to thank our pollution prevention program at Los Alamos for funding this work, and the High Explosives and Energetics program for procuring our instruments for us. This is Los Alamos. It's beautiful. We do have trees. And with that, I'll take questions.